All right, finally for our 2.6 part 1 notes, we are going to be looking at the center of mass and moment of a thin rod. So now what we are starting to do is we're starting to work into some three-dimensional type shapes. And we have a rod here. And on this rod, we can see that the center of mass is denoted by x bar. And rho of x is an equation that denotes the density. So I have that written down here. So rho is used to denote the mass density, which means the mass per unit of length. So that's what rho is going to stand for in this case. It's mass. So when we look at this, we're going to break up this rod into units, right? So just the same amount all the way down. And then each unit, the mass of each unit is equal to rho. So for today's homework assignment for part 1, rho is going to be a constant value. So rho of x is going to be equal to some constant value. The equation that we give you here is going to work when rho of x is an equation. We could give rho in terms of, oops, that's lovely. Come on, pen, don't do this to me. Rho of x could be equal to x squared plus x plus 3. So what that would tell us is that the density of the rod would change depending on the location x. So we will get to that in part 2. For part 1, all of our rhos are just going to be constants. But this is still the equation that we're going to use. So what this tells us here is little m is still going to represent our mass, sum of all of the masses put together. So we're defining this now in terms of integrals. We do not need integrals to define this. However, we are going to use integrals so that once we get to the equations and have to use integrals, we know how to use them. If that makes sense. So m is going to equal the integral from a to b of rho of x. So that's going to find the sum of all of the densities. So when we break these all up into little units, then the integral finds the sum from a to b of all of the unit measures of rho. And so that is just working with our density, our mass, total mass. And then capital M, just like we talked about before, capital M is going to be the density, or the mass times the position. So each one of these units is going to have a different position, right? And then it's also going to have a mass. Now when we're doing them in this homework assignment, all of those masses are going to be constant. But next part, where each mass is going to be different. So the moment is going to equal the sum of all of those masses times their position, and we can define that as an integral. So the integral from a to b of x, which x, if we were going to go through the definition of this, we would call each one of the positions of each one of these units x sub I. Say this one's x sub I sub plus 1, plus, and so on. And then when we take the integral and take the limit as we go, you end up with just taking the equation rho in terms of x dx. So these are going to be the two equations that we use to find our x bar, which our x bar is denoted here. So the position of the center of mass is equal to the integral of the position x times the mass, which in this case is the unit density, the sum of all of those between a to b over the integral of all of the masses, the total mass from a to b. And yep, so that is how we are going to find the center of mass of a rod. Moving on to example 4, this is what your questions are going to look like. So compute the center of mass, x bar, on a rod of density rho equals 4, with x being between -1 and 0. So let's draw a little bit of a picture here of what we're doing. Turn my right program on, there we go. So we can graph this bar. We're going to just revolve it around this x-axis here and say we have a bar that runs along here. And the position that we want to find the center of mass for is just from -1 to 0. So we just want to take this section of the bar. And find what the mass density, or the center of mass for that section. So to do that, we need to find m, which is equal to our total mass. So we're going to take the integral from a to b. Let's go ahead and just put those values in. From -1 to 0 of our unit mass, which is 4, and then dx. So this is going to find the sum of all of our masses, our total mass. So that will give us 4x evaluated from -1 to 0. So that's going to equal 4 times 0 minus 4 times -1, which is equal to 0 minus -4, which is equal to 4, which we could have guessed because what is rho? Rho is the mass of a unit, and we just are taking 1 unit of this bar. So 4 is what the mass, the total density for one section will be. Then the next one we need to find what the moment of the system is. Again, we're going from -1 to 0, but this time we need to multiply in the position. So the position is going to be x for each unit, and so we're going to find the sum of all of those units times 4, which is the mass for each one. And so that will equal 4 over 2x squared evaluated from -1 to 0, which is then going to be 2 times 0 squared minus 2 times -1 squared, which is then 0. That to become negative, so minus 2, which is equal to -2. Alright, so -2 is going to be our moment. Now our x bar, or our position, our center of mass, is going to happen at the moment divided by the total mass. So our moment in this case was -2 divided by 4, which then equals -1/2. So that tells me that the center of mass on this bar is going to be right at where x equals -1/2, which we could have guessed. We did not need calculus for this one, but it's a really good one to prove and to show you, I can't really say it's proof, but to show you how we can use calculus to identify where the center of mass is. All right, example number 5. Compute the center of mass, x bar, on a rod of density rho equals 3, with x being from 2 to 5. So again, let's draw a picture of what we are doing. And we have a rod running along our x-axis. And in this case, we want the section of rod from 2 to 5. So we are just looking at this section we'll just estimate it to be about that far. Okay, so that is all of the section of the rod that we are looking at. We want to know where the center of mass is. Again, do not need calculus, but we are using simple problems to start off with our calculus. So we want to know what the total mass is. So to figure out our total mass, we're going to take the integral of the mass of one unit, which is rho, from a to b of dx. In this case, we're going to have the integral from 2 to 5 of 3 dx, which is then going to equal 3x integrated from 2 to 5, which is then 3 times 5 minus 3 times 2, which is then equal to 9. Then we want to find our moment. Our moment is going to equal the integral from a to b of x, which represents the position, and rho, which represents the mass. So position times mass, which in this case is from 2 to 5 of x times 3 dx, which then integrating that, we have 3 halves x squared evaluated from 2 to 5. I'm going to go ahead and just leave my 3 halves out in front. Evaluate 25 minus 4, which is 21. So 63 over 2. So 21 times 3, 63 over 2. And then our center of mass is equal to x bar, which is the moment over the mass, which is 63 over 2 all over 9, which then invert and multiply. We would get 63 over 2 times 9, which then would become 7 halves, which is 3.5. So our center of mass is 3.5, which again should make complete sense. So right between 2 and 5, and the center of that would be 3.5. And that would be the center of mass for this. So part 2, we are going to be going deeper into this and start using some equations instead of just a constant rho value. We are going to be having some equations for that rho value. So we'll see you back in just a little while.